The name of this video is Electrostatic Dipole. In order to solve this problem, we can use all the information we learned in Phys 242. However, in Phys 342, in this course, we are going eventually to delve into details about the electrostatic dipole. So we will study the electrostatic dipole very much in detail, and why do we want to do that is because understanding the dipole is critical in order to understand dielectric materials. So let us consider a set of two point-like charged particles in space. So we have a discrete distribution of only just two point-like particles. So let us suppose that the first particle is here at this point. So this particle, we call it small q1. This is the charge associated with this particle, and it is located at the location capital Q1. This is the point in space where it is located. Somewhere here, we have a second particle, small q2, this is the charge associated with it, located at the point capital Q2. The question is, we want to find the electrostatic field at a point, for example, if this one is the line connecting these two particles, this is the midpoint of such a line, we want to find the electrostatic field, let's say, on this central axis. For example, at a point here, capital P in space. This is my observation point. As a limiting case, of course, you can also then find it at this point here, which is the midpoint of the segment connecting capital Q1 and capital Q2, and eventually I will ask you to do it everywhere in space. And this is something which I want you to discuss in Piazza. So we are trying to solve a problem where we need to find a vector. So we need to follow the usual procedure, which comprises 4 steps. The first step is to, in an inertial reference frame, like in this case, identify a suitable coordinate system. In this case, the suitable coordinate system is a Cartesian coordinate system, which I'm sketching here in green, as always. So, since eventually this is a 3-dimensional problem, allow me to use only 2 of the 3 coordinates of a 3-dimensional Cartesian coordinate system, where this one, we call it y, and this one, we call it z. And for the right-hand rule, x would be exiting in my direction of board, so this would be x. And in this case, this point coincides with the origin O, where which I set for this Cartesian coordinate system. So the first thing, Cartesian coordinate system. Now let's give a few dimensions here. This distance, these 2 points are equidistant from the origin, which means this distance is d12, and this distance is also d12. This height, which is the distance from the origin to this point capital P, is h. The second step of the procedure to find the electrostatic field in this case is to identify all the vectors associated with this discrete charge distribution. So we know that the electrostatic field has to fulfill Coulomb's law, and so we know that Q1 will generate a field along this direction connecting Q1 and P. So for example, since we don't know anything about Q1, let's hypothesize that this is the vector associated E1 with Q1. Similarly, because of Coulomb's law, Q2 will generate a vector in this direction connecting P with Q2. In this case, since we also don't know anything about Q2, let's say that this is the vector field E2 associated with Q2. So clearly, the third step is to identify the degrees of freedom associated with this problem. The degrees of freedom, obviously in this case, are 2, y and z, because whatever we do with these two vectors, when we sum them up, eventually we are going to find as DOF, degrees of freedom, the set y, comma, z. And so now we can finally use Coulomb's law for the electrostatic field, as well as the superposition principle, because we have a discrete distribution of two, a simple one, point-like particles in space. And so how do we proceed? We know from 242 that in this case, so first of all, we want to write down an electrostatic field in general in a Cartesian coordinate system. So in 3D, this would read as follows. E at any generic observation point capital P is given by the particle Q, let's give it an index I, could be 1 or 2, divided by 4 pi epsilon naught, as always. This quantity multiplies 3 components, x, y, and z. So we're going to have x, the x component of the observation point P, minus the x component of the source point Q. This has to go obviously along the x direction, ux, and just to make sure we are on the same page, ux is nothing but the unit vector along the x-axis, which in this case points towards me. Okay, in textbooks, typically nowadays people also call it just x with a hat. The reason why, again, I don't like it, because I work with quantum mechanics and hats represent quantum fields. So I like to use it to express it in this way, to write it in this way. So this is my notation. So ux is just unit vector, okay? The magnitude of ux is 1. And then I need to sum up the y contribution, which is y at the observation point P minus y at the source point Q, uy. And finally, the z component, which is z at the observation point P minus z at the source point Q times uz. In the denominator, we are using Coulomb's law, so we have the well-known factor of 3/2 coming up, and so in particular, this will be xp from Pythagorean theorem minus xq quantity square plus yp minus yq quantity square plus zp minus zq quantity square, the whole quantity power of 3/2, which we've seen in 342 many times. And this is our generic expression for one particle qi of the electrostatic field in a Cartesian coordinate system, which is the one we elected to use in this problem, which makes sense. All right, so now what are the coordinates of the various points which we need to use here associated with this distribution here? So for example, point q1 in this Cartesian coordinate system, x of course is 0, the x component is 0, the y component is minus d12, and the z component is again 0. Similarly, q2, which is the second source point, and here we need to sum up, of course. So here we want to eventually perform the sum of all these qi's over the index I. So that's why we need the coordinate for the second point, which again, x is 0. In this case, y is d12. And finally, z is 0. What about the observation point capital P, which is where we want to compute the electrostatic field? In this case, we have 0 for x as always, because we are in the yz plane. For y, we have 0 again, and the only term left is h, the height of that point. Good. Now we can substitute I equal 1 for the first point, 2 for the second point, and these various coordinates, P will remain the same because we are observing at the same point. Q obviously changes depending whether we are looking at the contribution from Q1 or Q2. It is simple to find out that the total electrostatic field, the sum is because of the superposition principle. So the final E at point capital P, well, let's begin. We are doing the superposition principle with Q1. So we're going to have small q1, which is the charge of the first particle, divided by 4 pi epsilon naught. So now we're focusing on q1, only this part here. Forget about that, only these 2 points. Okay, so in this case, all the x components are 0, so x will never be there in this case, and we know that makes sense because the degrees of freedom are only y and z, so we expected x not to be there. The y component of the p point is 0, the q component of the q point is minus the half, with a minus in front of it, it's plus the half. In the denominator, we have 0 for the x as always. This is the same, so it's d half. Which has to be squared now, from the Pythagorean theorem. And finally, for z, we have the z component of the p point, which is h, and the z component of the q point, which is 0, so it's nothing but small h, quantity squared, the whole quantity to the power of 3 half. And this goes along the u-y direction. Okay? So we only computing now the uy. So we only done this. In addition, there must be also a contribution from the z direction, which is what we are about to do now. So in the z direction, we have again q1 divided by 4 pi epsilon naught. In this case, however, we have 0 contribution from x. The y we already taken into account, so we're only looking at z. Z is h. We already computed here, so it's simply h. And in the denominator, we have, of course, the same quantity we found here. So d half squared plus h squared, power of 3 half. And this is our u, z contribution. The 2 degrees of freedom as expected, y and z. Y and z. However, this is only the contribution from q1. What about q2? Well, if we look at q2, for the y component, we noted that is exactly the same contribution as here, but now the location is plus the half, which means when we do minus the half, we pick up a minus sign, and this minus sign we can simply take it in front of the charge itself. So when linearly superimposed, we take this minus sign. This is positive, but we pick up a minus, we just put it in front of q2. Whereas here, in the case of uz, clearly there is no difference whatsoever between the two, so we just simply sum them up. Because in the z direction, zp is h, but zq is 0, and is 0 for both, so there is no sign in this case which we need to take into account. And so this is the linear superposition of the electrostatic fields due to the 2 particles, due to Coulomb's law, of course, and this is the final result which we find. Okay, so this is for any point capital P on this axis, because you can basically vary h if you want, and if you make it variable and you just call it z, if you just call this h a quantity z variable, then basically you found the electrostatic field everywhere on the z-axis. Now the first question I have for you for Piazza is what happens when h goes to 0? In other words, what happens when we attempt to calculate the electrostatic field right at this point here? That's one question. The other question I have for you is what happens if instead of considering a point capital P on that axis, on the z-axis, I consider a point capital P anywhere in space, so that the coordinates of this point are, let's say that x is still 0, so it's 0 still on this plane, y, z. So a generic point in the yz plane. So I want you to compute, this is the second question, I want you to compute E at a generic point 0, y, z. This is the quantity which I want you to compute. And in fact, I want you to plot it as well, which you can do very easily. I've done it a few minutes ago on Wolfram alpha when I calculated. For example, you can plot the amplitude of E. So let's be more specific. You can attempt to plot at every point y, z, the E magnitude, okay? So without vector. So these are questions which I would like you to address. So why these are important questions? Because you can start to think about the field lines associated with this construction of two charges. Okay, this is in general is an unbalanced electrostatic dipole because Q1 and Q2 can be different from each other. If they are the same, it becomes balanced, and then they can have opposite or equal sign, but it's still balanced with opposite signs. So I really want you that you start to think about the field lines associated with this system. So to give you an idea, if you solve all these problems, you will eventually should be able to find out that the field lines, let me sketch it down here. In fact, you can plot E, or you can also plot vectorially the field lines of E everywhere in space. You should really do both. So let me write actually both so that you really get a clear understanding of what's happening with this system. It's very important. I will tell you in a minute why it is so important, and I want you to do that. Well, in this case, the final answer, suppose for simplicity we assume a case where we have a balanced electrostatic dipole. This means that Q1 is equal to Q, and typically it also means that Q2 is not equal to Q, but is equal to minus Q. So typically we have opposite signs. So this is the most common example that we are going to encounter later on, and it's very important for dielectric materials. That's why I really want you to look into that, but also for another point which I will tell you in a minute. So it's important for two reasons. And so so suppose now that we have this scenario. So we have our charge plus Q, which I indicate with a full dot here, and then somewhere here a charge minus Q, which I indicate with an open dot. So this is plus Q, and this is minus Q, balanced but opposite signs. Okay, so in this configuration right there. That's what we're looking at. All right, so in this case, if you calculate E everywhere in space, you should be able to find the field lines, which will look like this. So here, if I put a positive test particle, it will move from plus Q to minus Q in this direction. So that eventually then I can plot this field line here like this, and then they start to curve like that, and more. Of course, all symmetric. Then eventually, they will come in this way. So these are the directions of all these field lines from the positive to the negative particle, this way. And obviously also here, we are going to go away, back into Q from infinite. And this construction is symmetric, so that's why it's okay to only do it above the two particles. It's symmetric below here. Okay, so that's important to note. So for example, if we represent this in a Cartesian coordinate system where this one is the z-axis, exactly as there. For example, if I pick this point here, at this point you should find out from this calculation that the electrostatic field only has a uy component. So it's tangent and it's directly along uy. Okay? So that's what you should find, for example. So why the electrostatic dipole is so important? One reason I already told you 2 times, because it's critical, this construction is critical to understand dielectric materials. Because dielectric materials are made of molecules which are positive and negative particles attached by a sort of a spring, and that's what defines dielectric materials, and by means of this definition we will be able in this course to understand the physics of dielectric materials. Okay, because they are molecules with positive and negative charges, with a spring in between, okay, so they are connected to each other. The other important reason is that in 242 we didn't cover a topic in conductors which is called the method of images. The method of images is a very powerful method which allows us to find the field distribution for complicated constructions such as a semi-infinite conducting slab, okay, with in front of it a single point-like particle. Okay, this seems a very innocent problem, but if you try to solve it by means of Poisson equation, it's super complicated. However, there is a trick where we can map this problem exactly to this very construction here. And the field lines will be exactly the same of these field lines here, with some caveats, which I will tell you later on. So you really need to understand exactly these field lines to understand the so-called method of images. So to recap this video, I introduce the electrostatic dipole, which you should be able to do from all the knowledge we acquired in the Phys 242, for two generic particles, Q1 and Q2, with different charge, linear superposition of Coulomb's law, in a Cartesian coordinate system, we find this result. I want you to, of course, investigate some limiting cases, for example, when h goes to 0. Most importantly, I want you to find this field everywhere on this YZ plane. And when you consider then the balanced case when Q1 is equal to Q and Q2 is minus Q, like the molecules of a dielectric material, also very important for the method of images, you should be able to find this field distribution down here. So that's what I want you to show me in a plot in Piazza. And that's it.